Okay. So, every test there'll be a little bit of reaching back to review some things. This year, what they're telling us has to be our emphasis is on solving equations. So we go back to the things where we solved equations. And there will be one absolute value equation like this, right, where it's an absolute value of an expression and it equals a number, basically, as opposed to the next one where it's an absolute value and it equals actually another algebraic expression, right? There's x's inside and out. So the first kind, there's only a variable inside. There's not going to be one outside, which makes it a little bit easier to solve, right? Now, all these questions, this first 5 questions, the ones that reach back and do review, are a multiple choice format. So you got strategies to solve them, right? You know how to take answers and plug them in and see which ones work. Right? If you do that, you'll get the right answer. Even if you don't remember all this stuff. I mean, I'm pointing you to this is how you really do it. But, I want us to be learning these strategies to get things right. So when we get to the SOL, it's secondhand, or second nature to have done it. Remember that when you solve an absolute value equation, the first step is you isolate the absolute value. This particular problem, it was already isolated, nothing to do, right? Second, you set the expression, which is inside, equal to 5. That's what they've done right here, right? And then you set it equal to -5, because if 2x minus 1 equals -5, what happens when you use the absolute value symbols? It equals 5, and so you got an equation. So that's why you set it equal to these 2 equations. Now, at that point, neither one of them has absolute value symbols on it anymore. Those are just 2 algebra equations you can solve like you solve algebra equations. So you add 1, divide by 2, you get x equals 3. Add 1, divide by 2, x equals -2. Right? We expect to get 2 answers for an absolute value equation. That's why. And of course, you can check. Okay. So, now, the procedures are the same. If there's variables inside and out, the procedures are still the same. You're going to set what's inside the absolute value equal to the right-hand side. That's that. But you're also going to set it equal to the opposite of the right-hand side. Just like on the last side, we did 5 and -5. Okay, here we're going to do 4x plus 5 and -4x plus 5. And you got to be careful to distribute the minus. Right? So it's -4x minus 5, and you solve. Just using basic algebra, solve, and get 2 answers like we expect. Right? But in these kinds of problems, and it'll say this on the test too, it says check for extraneous solutions. Because in this kind of problem, it's likely that one of the answers doesn't check. And it's not because you did anything wrong. But that's called an extraneous solution, and you got to throw it out. So in the check part of it down here, notice that when you plugged in the -3 in the original absolute value up here, they plug in -3 and -3, and then they simplify, and it does not, the left does not equal the right. It does not check, which tells you that the only answer is this one because it checked. Now, if you are in the process, just like plugging things in, you're not that the extraneous solution is not going to work for you. So you'll be correct in having thrown that one out if that's the way you're going to do it. Okay. You know what? This is missing one in there. Let me go to this. Insert page after. That is missing one. 46. And that one is like this. Right? I don't think that took. Solve absolute value less than. For example, 2x minus 1 is less than 5. The procedures are a little different when it's a less than or a greater than. Okay, so as always, isolate first, but that one is isolated, right? Then what? Then you got to turn, for a less than, you turn it into a three-part inequality, right? The three-part inequality looks like this. Go back to blue. Negative 5 is less than 2x minus 1 is less than 5. Right? It's this here goes in the middle. Right? There's the 5, and this is the opposite. It's telling you this expression inside can be in between negative 5 on the left and 5 on the right. Right? Because what if it's in between 0 and negative 5? When you take the absolute value, that puts it between 0 and 5, which is less than 5. Right? When you solve one of these, you solve for x in the middle. So in this case, add 1. Negative 4 is less than 2x is less than 6. Divide by 2. So negative 2 is less than x is less than 3. Okay, now that you graph, negative 2 will be on the left and 3 is on the right. Should I use open or closed circle? It's open because, yeah, it's not or equal to. So you're going to say open circle, and then where does the shading go? Notice, remember, this x here is represents the shading, and that shading is in between negative 2 on the left and 3 on the right. So the shading is here. Now, do you remember how you could put that in the calculator and have it make the graph? Because it is a graph. How do you put that in the calculator so it does the graph for you? Did I get that off the board? There we go. Y equals. Remember, how do we put the absolute value of 2x minus 1 is less than 5 up here? Okay, remember, for absolute value symbols, where do you find them? Yeah, I mean, it's in the catalog. I usually do math, hit the math, and then arrow over to the num, and it's number 1. But there are several ways to get there, but you should know how to find absolute value in the calculator. So you hit it, get it in there, and we want 2x minus 1 inside, so you do 2x minus 1. And then how do you get out of the absolute value symbols? Right arrow to get out. And now we need the symbol. Where do you find the symbol? The less than. Second math, right? It's the test menu. Second math. And those are all the options you've got. So we needed number 5. And that's less than 5. Right? So we just put that expression on the y equals. The fact is, we don't need the y, right? This thing does not have a y in it. So what it means to us is that when we look at the graph, don't worry about the y-axis. That's not really part of it. But if I look at this on a normal zoom 6, you know, you can see there it is. It looks like it's going from negative 2 on the left to positive 3 on the right. The shading is in between. Okay? Now, remember, if you look in the table of values, the table of values sometimes can be a help with this. Second, where's the table of values? Above the graph, right? Second graph. You know, and this thing, because you've got the integer values for x, everywhere that this thing is graphed, there's a 1, right? Everywhere that it's not in the solution, it's a 0. So you can see that it goes from, right, it goes from -1 to +2, right? Now, from the graph, you could tell it looks like it's going all the way to -2, but remember, that was an open circle on -2. It doesn't actually include the -2, right? It goes right up to it, but it does not include it. That's why it's still a 0. If that was a less than or equal to, it would have been a 1 for the -2. So also the 3, right? The 3, it looks like it's going right up to it, but it's not included, so it's a less than. Right. Write the equation for an absolute value function from the graph. So remember, the absolute value function looks like y is the absolute value of x. The question is, how do I, and the shape of that is a v. How do I shift that v by adding numbers and subtracting numbers? How do I make it go 2 to the left? Where? Okay, let me get rid of this. Right, this one would be y equals x plus 2 minus 3. Remember, inside is telling you the horizontal shift. Plus means left, minus means right. Since this thing is 2 to the left, that's where it is, right? And it's down 3 there. This is the vertical, that's the horizontal. So how would we show this one right here? Okay, so that would be a y equals x minus 2, and then what goes after? It's down 3. How do you show it down 3? Minus 3, right? Okay, how about this one? This one is right 2 up 3. How do I show right 2 up 3? X minus 2 plus 3. Okay, how about this one? This one is left 2 up 3. X plus 2 plus 3. Now, there's one, how would you make all those happen to be the same? They're all opened up. How would I make one of those open down? Yeah, if I put a negative in front of it, it would make it go down, right? If it had that right there. Those are the only transformations you have to worry about. There's only one problem, and it is a multiple choice format. You can always just put it in the calculator and look at the graph. Right. And then we move on to the stuff from this chapter, right? Which we just did some of this in the quiz. Put a polynomial in standard form and classify it by degree and number of terms. Right, meaning highest degree term to the left, descending order of powers, no parentheses, and then classify it. Right? If it's squared, you say quadratic. Right? Remember, here this was our table, right? Constant. These were the options we have: constant, linear, quadratic, cubic, quartic, and quintic. Above that, we usually just say 6th degree, 7th degree, whatever it is. But remember, this linear is x to the first, quadratic is x squared, cubic is x to the third, quartic is x to the fourth, quintic is x to the fifth. Right, and this one had some combining of like terms, right? the like terms are here. So we combine those and we write it in standard form. X to the fourth plus 10x squared minus 6x squared is 4x squared. Remember when you're doing these combining of like terms, right? Combining like terms never changes the exponent of x. There was some mistakes on the quiz, like when you added x to the third terms plus x to the third terms, you got x to the sixth terms. It doesn't. It stays the same. Right? And then this one, by degree, x to the fourth, you say quartic, and by number of terms, yeah, remember, these are our choices. Monomial, binomial, trinomial, polynomial. Right? This is one term. This is two terms. This is three terms. This is 4 plus. Good. Okay. Use the calculator to find the equation. A best fit, what do we call it? Best fit or regression equation. This one in particular, it says milk production. The chart shows how much milk Wisconsin dairy farms produced in 55, 80, and 2005. What linear model best suits the data, right? So remember, how do we put the data in the calculator? Stat edit, right? We already did that once when we did the quiz today. Now notice, and this is pretty typical, that when you've got years as being your X values, usually you don't say 2000 or 1900, and usually it's defined in the problem. This one says, you know, instead of putting 1955, 1980, put 55 and 80. Right? Just make it the years after 1900 instead of using the whole thing. I mean, you wouldn't be wrong if you put in the other, but you'd get a slightly different equation, that's for sure. Right? And then for 2005, then that becomes 105, right? Because it's 105 years since 1900. But for the rest of it, remember, you go stat edit and you put the X values in L1, the Y values in L2, and then you look at the data. Now, they told us, use a linear model. There was not even like, choose the right model. They just said, use a linear model. So here were their points, 1, 2, 3. And they used their linear model, or made their linear model. That would be this part right here. And then they drew it right in the middle of the data. Now, if you would looked at those points and chosen the model to use, would you have thought that was linear with that kind of a shape? I mean, you might have thought quadratic. I mean, it does look like there's a little bit of a shape to it right there. Right? If you did, remember, how would you choose quadratic instead of linear? Right? You would have gone stat calc 5 for quadratic, and you would have gotten a slightly different equation there, right? It's ax squared plus bx plus c with these coefficients. And of course, when you draw that one in your points, it's going to hit those points exactly. Because just like 2 points define a line, 3 points define a parabola. Right? So Remember, when we did this, and the way it'll be on the test, it won't tell you which function to use. Look at the data and decide, and then choose one of those four: linear, quadratic, cubic, or quartic. They're the only ones we've got. Now, their question in this is, looking at these two models, this is milk production since 1900. Which one looks more realistic? Would it be more realistic to think that milk production is doing this kind of thing? Or is it more realistic to think that it's doing this, which would mean actually there's no milk production right now? Probably in this case, quadratic is not the best description of that. Okay. Yeah, so remember, these are all your options. When you go to stat calc, then you're looking for these options here, just based on the shape. Right? Remember that if for linear, we're looking for something that's straight line. For quadratic, it could have one turn in it, something like that. For cubic, it can have two turning points in it, something like that. And for quartic, it could have three turning points, always one less than a degree. Okay, remember when we did this? Looking at the graph of a polynomial, how do you find the zeros? The Madison? The x-intercepts, right? Along the x-axis, so this one has zeros here, and here, and here. It looks like it's a cubic, and it's got 3 zeros, which we know now to be correct, right? This one looks like it's got 4. You know, you will have a graph and be asked to identify the zeros from the graph. So that should be an easy one for you, right? Just say what the zeros are that you see. Okay. How do we describe end behavior? Meaning, what is the graph doing on the extreme left side and extreme right side? Remember, we just did it in the homework last night. How did we describe the fact that this one started here and ended there? Yeah, we just said down and up, and that's fun. Down and then up. And this one was, on the left it is up and up. And this one is down and up. Right? That's another one, should be an easy one for you. This one is down and down. And then the last part of it is identifying where is the graph going up and where is the graph going down, right? Not to be confused with the end behavior. Let's go here. Right, this graph here has got 2 turning points in it, right? Here and here. So it's changing its behavior or its direction there and there. This one is changing its direction. Its turning points are here, here, and here. This one's got no turning points, and this one has got 1 turning point, which looks like it's about here. Okay, done. Right, so this, you say that the graph is increasing when it looks like it's going up from left to right. Right, so this is increase, this is decrease, this is increase. Right? Now, how do you describe where it's increasing or decreasing? With x values. The intervals are intervals of x. Right? So this thing is increasing from the far left side of the graph until it gets to which x value? -1. So you would say that it's increasing x less than -1. Right? And it's increasing again from +1 to the right. So how would we say that? X greater than 1. X value is greater than 1, this thing's going up. Now, the decreasing part is in here. decreasing. And we describe that one because we actually have numbers for the left and the right with a three-part inequality, just like when we do the absolute value functions, right? So this is -1 on the left and +1 on the right. Right, that's how we do those. Okay, from the factored form of a polynomial, identify the zeros and the multiplicity. So in this example here, they started with a standard form, but just looking at this one right here, what are the zeros? 4 and -2 and 0. Remember, when you have an x which is not plus or minus anything, then 0 is the 0. So the zeros are 0, -2, and 4. And why did I leave all that room next to the 0? Yeah, remember they said put in multiplicities if it's appropriate. In this case, that x is being squared. So how does that show up as a multiplicity comment? Right? It means multiplicity 2. Right? That does not apply to the -2 and the +4. And then just looking at the graph, I mean, the reason that we care about multiplicity is because we know when it's a multiplicity that's 2 or even, that if the 0 looks different on the graph. I mean, here are the zeros. We would have clearly said that's a 0, -2. That's a 0, +4. And then this one, 0 is the 0. But notice that this one, the graph actually touches x equals 0. And then it goes back on the same side of the x-axis. It doesn't pass right through the x-axis like the others. That's what happens when the multiplicity is even. Right? That's an important point. Okay, factors, sums, and differences of cubes. Now, for your problem, you have one problem like that. It is the 5th multiple choice question, right? And the reason I put it in there is because I want you to be looking at the pattern. You may not remember these formulas exactly, but you should remember when it's the sum or the difference of cubes, that what you get out of that is a binomial times a trinomial, right? It's 2 terms in parentheses times 3 terms in parentheses, right? And, you know, beyond that, if it's the sum of cubes, then that first, the binomial, that's a sum, right? These match. Plus matches with plus, minus matches with minus. And it's the next term which switches sign. So for the sum, that's a plus and that's a plus, but that's a minus. For the difference, that's a minus and that's a minus, but that's a plus. If you just recognize that pattern, you'll get this problem right. Now, just to, you know, if we were going to do this, let me solve this. All right, I'm going to use the pattern. First, what number cubed equals 64? 4, right? So if I consider this like x to the third plus 4 to the third, then what I've got here is x plus 4 times x squared minus 4x plus 16 equals 0. Okay, so we factor it so that we can use zero product property. Zero product property says that since a product equals 0, then one of the factors must be 0. Right? What is the 0 that's coming from the first factor? -4, right? -4 plus 4 would make that 0. So x equals -4 is the easy one. Okay. Whenever you have sum or difference of cubes, the trinomial is not factorable. The only way to solve it is with the quadratic formula. And what kind of answers do you expect? Imaginary. It'll be 2 imaginary solutions, because that's another good point. Imaginary solutions always occur in pairs, because where do they come from? Quadratic formula. Right, so you have to use quadratic formula to solve the trinomial. Right, this case, it'd be A is 1, B is -4, C is 16. So this will be x equals negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 16 divided by 2 times 1. X equals 4 plus or minus the square root of 16 minus 64, which is negative 48. And again, so now you see, this is going to be imaginary because you're taking the square root of a negative number. And 48 is not a perfect square. We've done this one a few times. So you factor it as 16 times 3. And the negative comes out as an I, right? Square root of negative 1 is I. So this one looks like x equals 4 plus or minus 4i times the square root of 3 over 2, which is 2 plus or minus 2i root 3. So it's an important thing. There is a question there that gets at the point that when you have a sum or a difference of cubes, that last, the trinomial there, 2 imaginary solutions, right? You expect 1 real, 2 imaginary. I'm going to skip over that one. Okay, solve a polynomial equation. I believe on your test, what it says is solve. It doesn't tell you how to solve it. You can solve any way you want, right? This one is definitely a factorable problem in terms of if you factored out the greatest common factor, which is x, what's left inside the parentheses is something you can factor. You go 2 times negative 3 is negative 6. Are there factors of negative 6 that add up to negative 5? Yes. That would be negative 6, positive 1, right? And you split up the middle term and group and factor, and you end up with this right here. How else could you solve that? How about graphing it? You know, what if you put this in the calculator? Y equals, like graph, y equals 2x to the third minus 5x squared minus 3x. And then where would you look for the zeros? We already did this. Okay, well let's do it then. Okay, here we go. Y equals clear 2x hat 3 minus 5x squared minus 3x. Okay, so let's see. Generally, when you're looking on a graph for the solutions, you're looking for what? The x-intercepts, right? And how many does it look like you see on this graph? You know, well, you definitely see this one at 3, and this display right here, the table of values is right there. And notice that in the table of values, if you did that, you would see at x equals 3, y equals 0. There's one answer, right? And then you see another solution in the table of values too, don't you? 0, right? At x equals 0, y equals 0, there's another. But it does look like that thing is going above the line there. If you zoom in, zoom to, enter, you can definitely see what's going on, right? It goes above, to the left of 0, it goes above, and then it comes back around through 0. You could probably estimate that as negative 1/2. You know, given that we've already got the answer right there, you know, that is the negative 1/2 that comes from that. How could I use the calculator to find that? That is another thing. using the calculator to find a 0 that's not in the table of values. We're going to do this on another slide, but remember, this is the second trace button, 2. Second trace, 2 for 0. And it's going to ask you those questions again. Left bound, right bound, and guess. And we know we're not interested in this 0. We got that one. We need this one. So the left bound has to be an x value which is less than that number, but on the screen. And this is the case I'd probably use the arrow keys. Hit the left arrow until you see that cursor go to the other side of the x-axis. Like that. Okay, that's a left bound. I mean, you left arrow to get to it, so it's a left bound. Hit enter. And for the right bound, you could use your right arrow to go to the other side of the x-axis. Like that. Hit enter. And then when it says guess, you always just say enter. I mean, if it doesn't work, you go back and try it again, but there's not any options to do anything else anyways, right? So just hit enter. And it goes right to the 0, which is -0.5, -1/2. So you can find it that way. Except, so on your question, on the Algebra 2 trig class, it says solve by factoring. They don't have a choice. But on this problem, if you want to solve it by graphing, by all means, solve it by graphing. Use the calculator to find all the zeros. So again, here we are again. So now if you weren't playing along, this is your chance to practice. Remember in the test, I can't send a calculator home with you to practice, so you want to practice it now. Put that in the calculator and see if you can find the zeros. Some are in the table of values and some are not. You get that much? Can you see the graph? How many zeros do you see? You see all 3 of them right there, right? Now, it looks like maybe one of them is at 1. How do you confirm that there is a 0 at 1? Go to the table of values, right? For the integer values, remember, how do you look in the table of values? Go second graph, and then look for the y equals 0 and x equals 1. That's one answer, right? But the other 2 zeros pretty clearly are not right at an integer value. They don't show up in the table of values, and it's pretty clear from the screen. They're in between. So that's where you got to go through that second trace to left bound, right bound guess. So try that on each of these zeros. Let's find the 2 that we didn't get. Let's get them. I'm doing the one on the left first. And I didn't use my arrow keys. I just entered x equals -5 for my left bound and x equals -1 for my right bound. Yeah. What is today? 11, 17. So what was that first one? Negative 2.645. Okay. And the next one. So now we already got the 1. So we're trying to find this one right there. And again, you could use your arrow keys to go to the left and the right of that. I'm just going to, for a left bound, I'm going to enter the number 2 because it's clearly to the left of the 0. 2, enter. And then for the right bound, I'll put in some number to the right. How about 5? So guess in between those 2 arrows? Sure. 2.64. One was a negative 2.64. The other one was a positive 2.64. Okay. So you know that's another one of these processes that you got to know. Unfortunately, I can't send the calculator home with you to get any work on it there. And then the last, I think this is my last slide right here. We're supposed to be able to tell from the degree of a function how many complex zeros does it have and how many possible imaginary and real solutions. And in these problems are the ones we did for homework. Remember, we're not doing the possible rational solutions. We're just doing real and imaginary and complex. So remember, how do you tell the number of complex zeros? Say again? By the degree, right? So this first one has a degree of 4. So how many complex zeros? 4, right? It's whatever is the degree, that's how many complex zeros. Right? So number of complex. Right. So this is the number 26, 4. Right. Now, what do we know about the number of imaginary solutions? There's one key fact about imaginary solutions. They what? Deshaun? They come in pairs. Remember that? Right? It's not too hard to remember, is it? They come in pairs because where do they come from? Quadratic formula. Okay, I've said that about 20 times in here. So a number of imaginary solutions right? If there's a total number of complex solutions, which is 4, then the number of imaginary has to be an even number less than or equal to 4, right? So what are the even numbers less than or equal to 4? 0, 2, and 4, right? So the possibilities are this, 0, 2, and 4, okay? The number of, remember, real numbers plus imaginary numbers make up complex numbers. So the number of real zeros has to be what's left, right? For example, if there's 4 complex zeros and none of them are imaginary, how many of them must be real? 4, right? The difference, right? These go together, right? If there's 2 imaginary, how many real? 2, right? And if there's 4 imaginary, how many real? None, right? Those are just possible. We didn't actually find any zeros, right? We just said these are the possibilities. Okay. Right. This is the study guide in terms of the pages and the problems. Again, you don't have to do them all, but you should be doing some from every group in order to make sure you understand what's being tested. I mean, I'd even recommend making yourself you could make yourself a little practice test by taking, a problem from each group and just doing it blind and seeing how you do. Right? Take an odd number you can check in the back of the book. And if you do a decent job of preparing by using the study guide, you can hand that in before the test, and I give you extra credit. All right? So if you fail the test, you could take a retest as long as you did the study guide and got full credit for it. Now, if you want to know more precisely what's going to be on the test, I mean, this is the same group of problems that it says exactly what you're doing, right? Solve absolute value equations. That's at page 46, 10 through 18, 19 through 21. The first group is the variables only inside the absolute value. The next one is variables inside and out, so check for extraneous, right? Solve the less than inequalities. That would be these problems. So these are more like the directions you're going to find on each problem. So you want to make sure you're getting that out of the study guide. What's I about to say? The things that are on here that are like, let's see. This one and this one, which is how do we put data in the calculator? How do we find the right function to model it with and do it? We'll go over that before the test. Since you don't have a chance to do it at home, we'll go over that right before the test. Same thing here. How do you find the zeros doing the second trace to that thing?